minus k over 2 pi z squared, right? Just differentiating with respect to z. This is what? This is u minus iv if you want the u and v, or if you want the vr and v theta, this is e to the negative I theta vr minus iv theta. Okay? So if I want the latter, these guys are e to the I theta z. So this is u infinity negative k over 2 pi r squared e to the negative 2 I theta. In order to extract these guys, I need e to the negative I theta as a common factor. So here I will have e to the I theta, and here I will have only one of these, because I took the other as a common factor. Okay? Now, the real part of this bracket is the radial component, and the imaginary part is negative differentiation. Okay? If you have a question, please stop me. So this is simply Vr minus I v theta. Let's get the real part. So the real part is u infinity cosine theta k over 2 pi r squared, also cosine theta, so I'll take it as a common factor. V theta is, I'll take the imaginary part now, so u infinity sine theta, minus minus is a plus, k over 2 pi r squared sine theta. And we have negative here because it's negative differentiation. Any question? So actually I didn't need to go over the way here to get the stagnation point, but anyway we will need these components later. You can get the stagnation point from here directly. This is the complex conjugate of the velocity to get a stagnation point, meaning all the components is 0. So just equate this guy to 0. So if you equate this guy to 0, you get immediately that z is plus or minus k over 2 pi u infinity, right? So it's a real. So the 2 points are here, one positive and one negative, and this tells you the radius. So this is the radius of the circle A. Okay? I did not show yet that this represents the flow around the cylinder. How to show that? How in all these things, I know it's not the focus of this course, but it's good to know. In all these cases, how to know that this flow represents the flow about half Rankine body, or here Rankine body, or here it's a cylinder. How to know that? How to know the constructed body? How to know that? Any idea? What characterizes the body?
Stagnation streamline.
This is great. This is exactly the thing. It's two pieces of information here. Well, the body has to be a streamline. Okay, so if psi is constant along the body, but if psi is constant along any streamline, what's the specific straight line that you need? It's the streamline passing through a stagnation point. So the first thing is to get the stagnation point. The first step is to get the point at which all velocities vanish. Here it is. Okay, so these 2 points are stagnation points. Get the stream function at this point. Let's get it. Let's get the stream function here. Well, the stream function is very easy. It's from f. I need the imaginary part of f, right? So actually this is r e to the I theta, r e to the I theta. So I need the imaginary part of this guy. So if psi is the imaginary part of f, it's u infinity r sine theta. This is the imaginary part. I'll take the sine theta as a common factor. Minus k over 2 pi r sine theta k. Right? So if you substitute these 2 points here, actually these 2 points are real. Theta is 0 and 1 theta is 180 pi. Both sine is 0. So if psi at the stagnation point is 0. So the equation if psi of x and y equals 0, this is the equation for your body. Okay? So here it is. So I'll set this to 0. U infinity r minus k over 2 pi r sine theta is 0 for all x and y's over the body. So this guy you can divide by, and you can get immediately here that r is constant, r squared is constant, and k over 2 pi u. What is the equation characterized by a constant radius? It's the circle, and this is its radius. So this is a squared, the radius of the circle. So this proves that the circle is a streamline due to this superposition. Uniform flow plus doublet indeed equals the circular circle. Okay? So you just need, in the homework I'll ask you, show that this body is a streamline. You just need to show that psi is constant along the body, and that's it. It's easy. Okay? Psi has to be constant along the body, of course. Any questions so far? Any question? So what's the velocity field? Well, here is your velocity field. Here is radial, tangential. At any point in the domain, I'm interested on my body. I'm interested when r equal this guy and for any theta. Okay? So on the cylinder where r is a is k over 2 pi u infinity, I have my v radial is, look at this here, when you substitute r squared by k over 2 pi u infinity, you get what? 0. Which makes sense. The radial velocity on the cylinder is 0 for sure. For the flow to be tangential, the flow has to be tangential along your body. The normal component is 0, right? So the radial component is 0. And what about v theta? Let's get v theta here again. On the cylinder, r squared over k over 2 pi u infinity. So you get 2u infinity here. Negative 2u infinity sine theta. The very famous equation, 2u infinity sine theta. And you can see immediately that this is symmetric. From which you can get the pressure. This is steady flow, so you can use Bernoulli equation to get the pressure coefficient. It will be 1 minus 4 sine squared theta. This means what? Here is the cylinder. So it means symmetric pressure distribution, right? It simply depends on sine squared theta. So here in the first quadrant, theta is positive. The sign here is exactly negative, the sign there. The sign here is exactly the same as the sign there, negative over here. But I don't care about the negatives. All these negatives I don't care because it's sine squared. So the distribution here is exactly like here, is exactly like here, is exactly like there. So when you integrate to get the forces, these two guys cancel each other, there is no drag, and these two guys cancel each other, there is no lift. Okay? Completely symmetric pressure distribution, there is no lift and no drag. Okay? I don't need to do it by mathematics. It's very clear from the distribution here. Okay? But you should be able to do it. The no drag, this is what we call the Dallenberg paradox. It's for, you should get drag anyway, right? You should get drag. There is friction. But from the beginning, we neglected the mechanism of the friction, which is rotationality. It's not only viscosity. Flow has to be rotational, right? It's mu viscosity multiplied by number squared u. This term depends on the rotationality. The boundary layer has rotationality in it. If you neglect rotationality, you know from the beginning that you're not going to get any spin friction drag. However, okay about that, we will account for it in a different way, in an indirect way, separately. Okay? But what about the lift? We didn't get any lift here. So we didn't get any drag because we neglected the rotationality, the viscous. shear due to omega. We neglected that already. We neglected omega. That's fine. We know that from the beginning. We were not interested in this compression drag. But what about the lift? We did everything here to get the lift over a flying object. This is the problem. And this is very deep problem. The potential flow would not be able to give you any lift whatsoever. Potential flow alone cannot give you lift. You have to add it yourself. So we'll say here, okay, the velocity distribution, pressure distribution is very symmetric. I have to add myself circulation. Remember, lift is due to what?